In this video, we're going to finish chapter 3 of the chemistry textbook. So chapter 3 is on mass relationships in chemical reactions. We started off by learning about masses at the atomic level. So atomic-sized particles, protons, neutrons, atoms, molecules. How do we measure and quantify masses at this scale? What units do we use? How do we relate masses and counts of particles at the atomic scale to the human size scale, the macro scale? So if we have a certain amount of substance in grams, so we can measure grams of substance in a lab, what does that mean in terms of the number of atoms or molecules that are contained within that substance? Okay, now we also talked about, with this understanding of masses at the atomic scale, how do we determine percent composition by mass of compounds? So what is the percent composition by mass of hydrogen in H2O, for example? And so now we want to finish off this chapter by applying our understanding of atomic scale masses to analyze the mass relationships in chemical reactions, which is the primary topic of this chapter. So in a chemical reaction, you've got one or more reactant compounds and one or more product compounds. What are the mass and count relationships in terms of reactants consumed or products produced? That's what we're going to talk about in this video. Okay, a basic question raised in the chemical laboratory is, how much product will be formed from specific amounts of starting materials or reactants? Or in some cases, we might ask the reverse question: how much starting material must be used to obtain a specific amount of product? To interpret a reaction quantitatively, we need to apply our knowledge of molar masses and the mole concept. Stoichiometry is the quantitative study of reactants and products in a chemical reaction. So stoichiometry, if you're doing stoichiometry, then you're quantitatively, so with numbers, analyzing the different amounts of reactants and or products associated with a chemical reaction. The amounts, right? So for a chemical reaction with a corresponding chemical equation, you're quantitatively analyzing things like how much of this reactant was consumed, and then correspondingly maybe how much of a certain product was produced based on the amount of that reactant consumed. Or you could look at it from the reverse direction. If a certain amount of product is going to be formed, then what amount of reactant must be consumed? And you can ask this about specific reactants or products. If there's 5 products in a reaction, well, okay, if we're going to produce this amount of this specific product, and then let's say there's a bunch of reactant compounds as well, then how much of this reactant is going to need to be consumed to produce this amount of this product? You're quantitatively analyzing these questions in stoichiometry. Now, the angle you look at any chemical equation, the perspective you look at it, so which reactants are you analyzing or which products, doesn't matter. Any kind of quantitative analysis of relationships between the amounts of reactants consumed and the amounts of products produced in a chemical reaction, chemical equation, that's stoichiometry. Okay, now it says whether the units given for reactants or products are moles, grams, liters, so liters for gases, or some other units, we use moles to calculate the amount of product formed in a reaction. This approach is called the mole method, which means simply that the stoichiometric coefficients in a chemical equation can be interpreted as the number of moles of each substance. Okay, so what are they saying here? All right, again, so what we're doing in stoichiometry, we're analyzing the relationships between the amounts of reactants and products. Well, the term amount, the amount of a substance, amount of a compound, can be applied in different perspectives, meaning an amount in the sense of a certain count of molecules or atoms, or maybe an amount in terms of a certain mass of a substance or compound, or an amount from the perspective of a certain volume of a compound, right? However, what they're saying here about the mole method, what they're talking about, and that we use the mole method, they're talking about from the perspective of the chemical equation of a chemical reaction, right? This is for any given chemical reaction, this is the main way that we model what's taking place in the chemical reaction with a chemical equation. Well, we know that when we're looking at a chemical equation, if we're going to read a chemical equation from left to right, use a chemical equation to describe a chemical reaction to somebody, then what we're describing is from the atomic or molecular perspective. What I mean is, if I'm going to describe this chemical reaction to you, we know that, so what this is saying is that one way you could describe this is a molecule of N2 gas reacts with 3 molecules of H2 gas to produce 2 molecules of NH3 gas, right? That's exactly how we interpret what this chemical equation is saying, and it shows it graphically here. One way of looking at what this is saying from a molecular perspective is, so you've got these 3 molecules of H2 gas, there's the 2 H2s, the 2 hydrogens on each molecule, are going to come together with 1 molecule of N2 gas to produce 2 molecules of NH3 gas. And so there's the 2 nitrogens, and then there's the 6 total hydrogens, right? We started with 6 total hydrogens, 2 total nitrogens, and we can account for where they all went. Okay, but we could just as easily have described this chemical reaction, this chemical equation, using moles. It makes perfect sense to, instead of saying this one molecule at a time, to just say, okay, since we know that the actual human size scale chemical reaction involves thousands of trillions of molecules like this, then we could just say, okay, we could look at this as you have 1 mole of N2 gas molecules are kind of all interacting with 3 moles of H2 gas molecules to produce 2 moles of NH3 gas molecules. That makes perfect sense. And you might be scratching your head a little bit thinking, well, no, we can't just change that to moles, can we? Absolutely we can. Remember, moles is just a scaling factor. It would be like saying, okay, instead of moles, we're going to use dozen. Would it make sense to say, okay, you have a dozen N2 gas molecules are interacting with 3 dozen H2 gas molecules to produce 2 dozen NH3 gas molecules? Well, of course that makes sense. All you're saying is just, okay, you have these 3 H2 molecules, just turn that into 36. So now you have 36 of these, but to make it accurate, we need to scale the N2 molecules up the same amount. So we need to put 12 of these N2 molecules. And then to make it make sense, you just scale the 2 NH3 molecules up by the same amount. So we need 24 of these. It makes perfect sense. The only way it kind of wouldn't make sense is if, in actuality, you didn't have that many of these molecules interacting with one another, right? If in actuality, you only really had 3 of these H2 molecules and 1 of these N2 molecules, and you're producing 2 molecules, and that's it, well, then it's like, okay, well, you're visualizing too many molecules interacting. But in reality, no, there are hundreds of thousands of trillions of molecules interacting. So it does make sense to not just say dozens, but to say moles. Makes perfect sense, right? So you see how when we use moles, when we describe this in moles, it is the exact same thing as describing this 1 molecule or 3 molecules at a time. We just scaled it up. And so that's what they're talking about here with the mole method. When it comes to any chemical reaction, chemical equation, sort of the bedrock starting point, the foundation, is we view the equation from a molecule or atom perspective, or equivalently from a mole perspective. And really from the mole perspective is more of the heart of how we do stoichiometry with chemical reactions, because the mole is more of our direct tie to macro-sized measurements like the gram, right? If we're talking about a chemical equation in terms of moles, then now we have more of that direct tie to grams, right? And then from grams, once we have something in grams, we can convert that to any mass we want, right? Go to the Google built-in unit converter. Once you have a measure of something in any unit, you can easily just convert to whatever unit you want. It's just a unit. But our direct bridge from the macro human-sized world to the atomic-sized world is through the mole and the gram. So in general, the idea is we're going to convert counts and masses to moles and grams, cross that bridge, and then once we've crossed the bridge, we can convert back to whatever we want. Okay, so the stoichiometric coefficients show that one molecule of N2 reacts with 3 molecules of H2 to form 2 molecules of NH3. It follows that the relative numbers of moles are the same as the relative numbers of molecules, 100%. That should make perfect sense to you. All we've done with the mole is just scale everything up by the same factor, like we would do if we described this in terms of dozens. With moles, we're still just talking about counts of molecules, counts, which is exactly what the chemical equation is based on, counts. A certain count of N2 molecules reacts with a certain count of H2 molecules to produce a certain count of NH3 molecules. Okay, thus, this equation can also be read as 1 mole of N2 gas combines with 3 moles of H2 gas to form 2 moles of NH3 gas. In stoichiometric calculations, we say that 3 moles of H2 are equivalent to 2 moles of NH3. That is, so 3 moles of H2 are, this is called a stoichiometric equivalency to 2 moles of NH3, where the symbol means stoichiometrically equivalent to or simply equivalent to. This relationship enables us to write these conversion factors. So what they're talking about here is, okay, so we've got so when doing stoichiometry, you're going to make use of what they're calling these stoichiometric equivalencies. You're going to use these equivalencies like conversion factor, but they're not actually true conversion factors. That's why they have this, it's a stoichiometric equivalency. So a conversion factor is, you say, so 1 foot is equal to 12 inches. So now if you have something like, okay, you want to convert 144 inches, you want to see how many feet that is, well then you would say, okay, you'd use the conversion factor. There's 12 inches in 1 foot. You put inches in the denominator, so these will cancel, and you're left with feet. 144 divided by 12 feet. But you can go the other direction as well, right? An equality goes in both directions. If you want to convert from feet to inches, then, so 20 feet, how many inches is that? Then you would say 1 foot. There you go. That's how we're going to use these stoichiometric equivalencies when doing stoichiometry. Okay, but what are these equivalencies? Well, they apply to any balanced chemical equation, and you can only have these stoichiometric equivalencies with respect to moles or atoms or molecules. You could do this in dozens, but with respect to counts of atoms or molecules, so a certain count of N2 molecules, which is typically going to be moles, is stoichiometrically equivalent to a certain count of NH3 molecules. And these counts are based on the coefficients. You're going to say 1 mole of N2 molecules, once this is balanced, is stoichiometrically equivalent to 2 moles of NH3 molecules. Or you could say it in reverse if you want to, like the equality goes both ways. With any balanced chemical equation, if you have all of the reactants and products accounted for and it's balanced, then all of the reactants, all of the products, or all of the mixing of reactants and products, they're all stoichiometrically equivalent to one another in terms of moles. The number of moles based on the coefficient, right? This would be 3 moles of H2, 2 moles of NH3, 1 mole of N2, right? 3 moles of H2 is stoichiometrically equivalent to 2 moles of NH3. You say the coefficient of that many moles or whatever count you want of that molecule, that reactant or product is stoichiometrically equivalent to, then you say the coefficient of that many moles of whatever other reactant or product you want. Everything in a balanced chemical equation, everything is, from the count mole perspective, everything is stoichiometrically equivalent to everything. Okay, but why is that? What does that mean? All that means is that you're just making the statement that, okay, when this reaction takes place, for every 3 moles of H2 molecules consumed, 2 moles of NH3 molecules are produced. Or you could say that from the reverse. You could say for every 2 moles of NH3 molecules produced, 3 moles of H2 molecules are consumed. So they're stoichiometrically equivalent. Or you could say, you could do this between any of the compounds involved anywhere in the reaction. So for every 1 mole, or you could say for every 1 N2 molecule consumed, 3 H2 molecules or 3 moles of H2 molecules are consumed, right? We just stated the stoichiometric equivalency between the two reactants. Or for every 1 mole of N2 molecules consumed, 2 moles of NH3 molecules are produced. If there was some other product, you could state stoichiometric equivalencies between the reactants and the products, or between the two products. Okay, but now, what's the purpose of these stoichiometric equivalencies? How do we use them to do stoichiometry? Well, their main use is because for an actual chemical reaction that takes place, a reaction that we're analyzing in a lab or in nature, etc., in general, the reaction isn't going to involve the exact amounts shown in the chemical equation, right? You're not always going to have a case where you're thinking about, okay, I'm going to start with 3 moles of hydrogen gas and then let this reaction take place. So with that, how many moles of N2 gas were consumed and how many moles of NH3 gas were produced? No, in general, you would say something like this. You would say, let's consider a simple example in which 6 moles of H2 react completely with the nitrogen gas to form ammonia gas, right? And so in this case, in order to calculate the amount of ammonia produced or nitrogen consumed, we're going to need to use the stoichiometric equivalencies, sort of as conversion factors. So if we start with 6 moles of hydrogen gas, and now we want to sort of convert this to some other compound in this reaction, whatever compound we want, we use the stoichiometric equivalency. So if we're trying to calculate the number of moles of ammonia produced, then we're going to use the stoichiometric equivalency between, so we want to incorporate hydrogen gas for sure, but then we're asking about the ammonia. So the equivalency of, for every 3 moles of hydrogen gas consumed, 2 moles of NH3 are produced. Those cancel, and so now the units are moles of NH3 produced, which is what we're looking for. 4 moles of NH3 produced, just like that. But we could have converted this moles of H2 consumed to any reactant or product. If there was multiple reactants or multiple products, we could have converted this to whatever we want, right? Because everything is stoichiometrically equivalent to everything in terms of moles or any kind of count of the compounds, right? So just for example, if we wanted to say, okay, if 6 moles of hydrogen gas are consumed in this reaction, well then how many moles of nitrogen gas did the hydrogen gas react with? Okay, well, for every 3 moles of H2 consumed, 1 mole of N2 is consumed. There you go. So it's 2 moles of N2 consumed. You see? Okay, but now in many circumstances, in the lab or in the environment, in an industrial process, etc., we're going to have quantity information about reactants or about a certain amount of product we are planning to produce with respect to mass, right? We can directly measure masses. We buy reactants. We'll purchase nitrogen gas, hydrogen gas, or other reactants in terms of mass. So what if we're asked, it says, suppose 16 grams of H2 react completely with N2 to form NH3. How many grams of NH3 will be formed? Well, how do we answer this question? Well, it's not a big deal. It's not a big deal because we have that bridge between moles and grams, right? Because we do stoichiometry fundamentally with moles. That's where all of the stoichiometric equivalencies are. That's how we can go from a reactant to another reactant or to a product or etc. We can move anywhere we want in the chemical equation using the stoichiometric equivalencies in moles. But how do we get to moles? Well, we first want to get to grams. And then with grams, we can use molar masses to get to moles. Then we convert to whatever reactant or product we want. Then we'll be in moles of that reactant or product we're interested in. And then we can convert back to grams. And then, but once we're in grams, we can convert to whatever mass we want, even if we're given a certain mass to start with, in pounds mass or slugs or tons, etc. That's still not a problem because we just convert to grams, use molar mass to convert to moles, use the stoichiometric equivalencies to get in terms of whatever product or reactant we're interested in. Then we're in moles of that product or reactant, use molar mass to convert back to grams, and then if we want to go from grams to some other mass unit, then just do a conversion. So if we start off with 16 grams of H2, okay, so we're trying to find out the grams of ammonia produced from 16 grams of H2. Well, we cannot just say something like, for every 3 grams of H2 produced, 2 grams of NH3 are produced. Or for every 3 grams of H2 consumed, 2 grams of NH3 are produced. No, that's not the stoichiometric equivalency. It's in terms of moles. So we need to first convert to moles of hydrogen gas. Well, we know the molecular weight of H2 is going to be, you have 2.016 grams of H2 for every 1 mole of H2. Right? That's a fact. The molecular weight of H2 in AMU is also equal to its molar mass. For every 2.016 grams of hydrogen gas, H2 gas, there's going to be 1 mole of H2 molecules. So now we're in terms of H2 molecules. And we can use the stoichiometric equivalency. For every 3 moles of H2 molecules consumed in this reaction, 2 moles of NH3 molecules are produced. So now we're in moles of NH3 molecules, NH3 gas molecules, in moles. But we're wanting to know the grams of NH3. Well, we just use the molar mass of the NH3 molecule, which is just it's the same quantity as the molecular weight, right? So that's what they do here. It's the molar mass of NH3 is 17.03, and there's the grams of ammonia produced from 16 grams of H2, and they combine, here's the full chain. You start with 16 grams of H2, convert to moles of H2, stoichiometric equivalency, now convert to grams of NH3 with the molar mass of NH3. Right, so since 16 grams of H2 were converted to 90.1 grams of NH3, you could say that in terms of stoichiometric equivalency of the amounts of these substances in grams, you could say that these two are stoichiometrically equivalent. So like if you divide both sides by 16, then you get, so 1 gram of hydrogen gas is stoichiometrically equivalent to 5.63 grams of NH3. So this technically is true. Because for this particular reaction here, this chemical reaction, for every 1 gram of hydrogen gas consumed, 5.63 grams of ammonia gas are produced. However, we don't look at stoichiometric equivalencies this way in terms of grams, because it's not in parallel with the way chemical equations are written and interpreted. Chemical equations are balanced and interpreted in terms of counts of atoms and molecules, right? So the stoichiometric equivalencies are in line with chemical equations. Okay, now it says we could have done a similar process with grams of N2 that reacted with this 16 grams of H2. And so it's really simple. You just start by converting to the 16 grams to moles of H2, but now you use a different stoichiometric equivalency. Because in this case, you want to go to the other reactant, the N2. So then you're in moles of N2. Now convert to grams of N2, and you've got 74.1 grams of N2. So in this reaction, 16 grams of H2 reacted with 74.1 grams of N2 to produce 90.1 grams of NH3. Okay, so it says the general approach for solving stoichiometry problems is summarized as write a balanced equation for the reaction, convert the given amount of the reactant in grams or other units to moles, use the mole ratio from the balanced equation to calculate the number of moles of product formed, then convert the moles of product to grams or other units of product. Yeah, so again, you have some balanced chemical equation. It's fully balanced. It's a full, proper chemical equation with all of the reactants and products properly accounted for. Now, from there, you have some information about a certain amount of reactant that's going to be used, or a certain amount of product that you're hypothetically thinking about being formed. And this amount of reactant or product could be in any mass unit, or maybe it's in volume, and then you use density, mass per volume, to get to mass. Okay, from there, if you're wanting to analyze based on this amount of reactant or product, then what's the corresponding amount of some other reactant or product that's going to be consumed or produced? Then you convert the mass you have to grams. Maybe you started with a volume of material, so you use density, mass per volume, to get the mass of the substance you have, then convert that mass to grams. Now, using molar mass, you can convert that mass in grams to moles, then use the stoichiometric equivalency you need to convert from moles of that substance you started off with to moles of the other substance, reactant, or product that you're wanting to find quantity information about, then use the molar mass of that other substance to convert to grams of that other substance consumed or produced in the reaction. And then from there, you can convert that mass in grams to any mass you want. Or you could convert to volume with density going in the other direction if you want. Okay, but now, to be able to fully analyze any chemical reaction, chemical equation with stoichiometry, there's something else we need to consider. So, okay, let's say we have the reaction. Okay, and so as we just saw with stoichiometry, in general, you're going to have a chemical reaction, a chemical equation you're analyzing, and also some specific circumstances. Like, okay, we're going to start with a certain amount of hydrogen gas, or a certain amount of nitrogen gas, or we want to hypothetically think about a certain amount of ammonia gas being produced. And so what we're going to need to consider is, for some specific case, is there a limiting reagent? And if there is, what is it? Okay, so it says when a chemist carries out a reaction, the reactants are usually not present in exact stoichiometric amounts. That is, in the proportions indicated by the balanced equation. Yeah, exactly. You could think about how For any general chemical reaction that's carried out in a laboratory or in an industrial process, it's going to be the case that most of the time, if you're analyzing, okay, we're putting in this many grams of this reactant or that reactant, etc., most of the time that amount of grams is not going to be just the right amount. It's where every one of those molecules reacts perfectly with all of the other reactant molecules, to where all of the reactants are completely consumed and convert perfectly into products. If that was the case, then that's what they're talking about, how all of the reactants would have been present in the stoichiometric amounts. Everything would be perfectly balanced. Okay, it says, because the goal of a reaction is to produce the maximum quantity of a useful compound from the starting materials, frequently a large excess of one reactant is supplied to ensure that the more expensive reactant is completely converted to the desired product. Consequently, some reactant will be left over at the end of the reaction. The reactant used up first in a reaction is called the limiting reagent, because the maximum amount of product formed depends on how much of this reactant was originally present. When this reactant is used up, no more product can be formed. Excess reagents are the reactants present in quantities greater than necessary to react with the quantity of the limiting reagent. So yeah, what they're saying here is that for general chemical reactions that are taking place in a laboratory or even in natural biological processes or in nature, if you're stoichiometrically analyzing that reaction, most of the time it's going to be the case that the reaction is going to stop and there's going to be leftover reactants, right? A chemical reaction can't take place without all of the reactants present. And so if one of those reactants runs out, then the reaction stops. And you're just left with this excess reactant as well as product that formed when the reactant that ran out was still present. Okay, the reactant that runs out, which in general is going to be a single reactant, unless it happens to be the case that there's more than just one reactant that are perfectly present in the stoichiometric amount, but usually that's not going to be the case. Usually there's going to be just one reactant that's going to run out first and cause the reaction to stop. That's called the limiting reagent. And then all of the other reactants that are left over are called the excess reagents. Okay, so note how with this topic of limiting reagents and excess reagents, we're talking about the reactants of a chemical reaction. You can't have a limiting reagent or excess reagent in the products of a reaction. We're focusing on reactants here. Okay, so consider the industrial synthesis of methanol from carbon monoxide and hydrogen at high temperatures. So here's the balanced equation. Suppose initially we have 4 moles of carbon monoxide and 6 moles of hydrogen gas. One way to determine which of the two reactants is the limiting reagent is to calculate the number of moles of methanol obtained based on the initial quantities of carbon monoxide and hydrogen gas. Yeah, so you can use your intuition here to figure out how you would analyze to see which reactant, if any, is the limiting reagent. Okay, so they're saying if we're going to start with 4 moles of carbon monoxide and 6 moles of hydrogen gas, and so you can think about that they could have given us these quantities in grams of carbon monoxide and grams of hydrogen gas, and then we could have just converted to moles, right? Okay, but we can do a simple thought exercise here to get a sense for this. For every 2 molecules of hydrogen gas consumed, 1 molecule of carbon monoxide is consumed. So, all right, if we think about 4 molecules of carbon monoxide and 6 molecules of hydrogen gas, so 2 molecules of hydrogen gas go away. So we have 4 left, and that means 1 molecule of carbon monoxide was consumed. All right, now 2 more molecules of H2 are consumed, and that results in 1 molecule of carbon monoxide being consumed. Now another 2 H2 molecules consumed, 1 carbon monoxide consumed, and so there you go. The hydrogen gas is the limiting reagent. if you start with 4 moles of carbon monoxide and 6 moles of hydrogen gas, the hydrogen gas is going to run out first. Well, how is that possible? You start off with more moles of hydrogen gas than carbon monoxide. Yeah, but for every 1 molecule of carbon monoxide, you're going to need 2 molecules of hydrogen gas to create the methanol. So the stoichiometric amount here would be 4 moles of carbon monoxide to 8 moles of hydrogen gas. That would be the perfect stoichiometric amount to where you'd have no limiting reagent. And then if you had more than 8 moles of hydrogen gas and still 4 moles of carbon monoxide, then the carbon monoxide would be the limiting reagent. Okay, and so now the way that the textbook analyzes this is they assume that, so if all 4 moles of the carbon monoxide were converted to product, assuming you had excess hydrogen gas to work with, there was no issue with the hydrogen gas being limiting, then you use the stoichiometric equivalency to show that there would be 4 moles of methanol produced. Now, the same idea with the hydrogen gas. If all 6 of the moles of hydrogen gas were completely converted to methanol with no issue of running out of carbon monoxide, then you would produce 3 moles of methanol. And so you can see how this shows you that the 6 moles of hydrogen gas is going to be limiting, because you can produce more product with 4 moles of carbon monoxide than you can with 6 moles of hydrogen gas. So there's different ways of analyzing the reaction to see which reagent is limiting. And so in stoichiometric calculations involving limiting reagents, the first step is to decide which reactant is the limiting reagent. After the limiting reagent has been identified, the rest of the problem can be solved with everything we've talked about in this video. Yeah, so to stoichiometrically analyze any chemical reaction, you use all of the methods we talked about in the first part of this video. But before you start doing the stoichiometry, you need to analyze the whole system to see if there's any limiting reagents. Because if there is, then your stoichiometry is going to have to go through the amount of limiting reagent consumed. You can't do the stoichiometry and go through the amount of an excess reagent you started with, because not all of that amount reacted in the chemical equation. So you're going to get incorrect answers. Okay, so it says, in practice, chemists usually choose the more expensive chemical as the limiting reagent, so that all or most of it will be converted to products in the reaction. So in the previous example, we're not going to go through these examples here. We'll work a bunch of practice problems in the upcoming videos. In the previous example involving the synthesis of urea, NH3 is invariably the limiting reagent because it is more expensive than CO2. Yeah, so you can think about how if you have a chemical reaction in, let's say, some industrial process, and one of the reactants is expensive, then you're going to design the process to where that reactant is fully consumed in the reaction. And you do that by making sure that that reactant is the limiting reagent, with the less expensive reactants being the excess reagents. Now it says, at other times, an excess of one reagent is used to help drive the reaction to completion, or to compensate for a side reaction that consumes that reagent. Yeah, so we're going to learn in later chapters about rates of chemical reactions. So maybe it's the case that if you let a reaction take place at close to the stoichiometric amounts, then the reaction is very slow. Or like it says here, maybe there's these slight side reactions taking place. Or maybe the reaction is slightly reversible. It goes in both directions. And at the same time, you're really trying to maximize the amount of a certain product that's coming out of the reaction. You're trying to maximize the yield. So what you might do is add in a lot of an excess reagent that maybe isn't very expensive to really push the reaction towards the products. We're going to see that big concentration differences between reactants and products can increase rates of reaction and at the same time maximize yield. So they're just trying to give you a sense here of some of the reasons you might see excess reagents and therefore limiting reagents involved in chemical reactions. Okay, so synthetic chemists often have to calculate the amount of reagents to use based on this need to have one or more components in excess, as the next example shows. So let's take a look at this example. Okay, the reaction between alcohols and halogen compounds to form ethers is important in organic chemistry, as illustrated here for the reaction between methanol and methyl bromide to form dimethyl ether, which is a useful precursor to other organic compounds in an aerosol propellant. So here's the balanced chemical equation. This reaction is carried out in a dry or water-free organic solvent, and the butyl lithium serves to remove a hydrogen ion from methanol. Butyl lithium will also react with any residual water in the solvent, so the reaction is typically carried out with 2.5 molar equivalents of that reagent. How many grams of methyl bromide and butyl lithium will be needed to carry out the preceding reaction with 10 grams of methanol? Okay, so we're not going to go through all the calculations here, but I'm just trying to give you a sense for the application of an excess reagent. What they're saying is that in this reaction, ideally this reaction should be carried out in a completely water-free environment. However, in practice, the environment isn't going to be fully water-free, and so what happens is this butyl lithium, which has a definite purpose in the reaction, right? If you run out of butyl lithium, then the reaction can't take place because it removes a hydrogen ion from the methanol. Okay, but the butyl lithium will also react with any residual water in the solvent. So if you added the perfect stoichiometric amount of butyl lithium, then the reaction isn't going to go to completion with the corresponding stoichiometric amounts of methyl bromide and methanol, because some of that butyl lithium is going to react with the slight traces of water present. So what they do is they just add excess butyl lithium to make sure that all of the methanol and all of the methyl bromide present fully reacts. And so now all this question is really asking is, it's kind of a simple question. If you start with 10 grams of methanol, how many grams of methyl bromide do you need? Well, if you have an excess of the butyl lithium, well, then they're just saying, okay, calculate the corresponding stoichiometric amount of methyl bromide that corresponds to 10 grams of methanol. Okay, and so what you can see is, in a lot of cases with chemical reactions, we're concerned about the yield of a certain product, right? In a lot of cases, we want to maximize the yield. We want to design the whole chemical reaction to where the yield of a certain product is maximized. So the amount of limiting reagent present at the start of a reaction determines the theoretical yield of the reaction. That is, the amount of product that would result if all the limiting reagent reacted. Yeah, so the theoretical yield is not saying that if there wasn't a limiting reagent, then how much of a certain product would be produced. That's not what theoretical yield is saying. No, it's saying that once you've determined the limiting reagent, then assuming that the reaction goes perfectly to where all of the limiting reagent is consumed and fully converted to one of the products that you're interested in, right? There could be multiple products, but when it comes to calculating a yield value, we're focusing on a certain product. Okay, the theoretical yield is, again, all of the limiting reagent is consumed and is sort of perfectly converted to the maximum amount of a certain product. That is the theoretical yield. The theoretical yield is the maximum obtainable yield predicted by the balanced equation. But in practice, the actual yield, or the amount of product actually obtained from a reaction, is almost always less than the theoretical yield. Yeah, exactly. The actual yield would be the reaction is complete, everything is shut down, everything's done, and you take all of the product that you were trying to obtain and weigh it. Whatever it weighs, that's the actual yield. What they're saying is it's almost always going to be the case that the actual yield is going to be less than the theoretical yield. Again, we're not saying that the theoretical yield is if everything was present in the stoichiometric amount. That's not what we're saying. No, you can imagine, let's say there's some gold mining process with a really important chemical process that separates out the gold from the ore, right? This whole process has a chemical reaction associated with it, but the reaction is designed with excess reagents because maybe there's an expensive reactant that they put into the process that they want to make sure is fully consumed. Okay, and then output is a bunch of different products, with one of those being pure gold. Okay, well, when it comes to calculating yield, you're focused on the amount of gold that comes out of the process, right? The theoretical yield is saying, look, if I put this much reactants into the process, then even with the limiting reagent, theoretically, if everything goes perfectly to plan, this amount of gold should come out. Okay, but we all know in actuality, processes don't go perfectly. When you actually take all of the gold, when everything's finished and you actually take all of the gold that came out and weigh it, almost always you're going to have less gold than you theoretically should have had. That's the difference between theoretical and actual yield. So there are many reasons for the difference between actual and theoretical yields. For instance, many reactions are reversible, and so they do not proceed 100% from left to right. Even when a reaction is 100% complete, it may be difficult to recover all of the product from the reaction medium, say from an aqueous solution. Or maybe there's some product sort of caked into the walls of the container. Some reactions are complex in the sense that the products formed may react further among themselves or with the reactants to form still other products. These additional reactions will reduce the yield of the first reaction. Okay, to determine how efficient a given reaction is, chemists often figure the percent yield, which describes the proportion of the actual yield to the theoretical yield. Yeah, so okay, percent yield of a reaction is just the actual yield divided by the theoretical yield times 100%. Percent yields may range from a fraction of 1% to 100%. Chemists strive to maximize the percent yield in a reaction. Factors that can affect the percent yield include temperature and pressure. We will study these effects later. Yeah, so you can think about how a practicing professional chemist, one of the reasons that they could be hired by a big company, by a big entrepreneur, is because the entrepreneur wants to maximize the yield of a chemical reaction, right? If you think about the TV show Breaking Bad, Walter White he's such a good chemist that he can maximize the yield of the methamphetamine production process. Disclaimer that that's just a TV show. Please don't start cooking methamphetamine. Walter White's life is completely ruined at the end of the show, so please don't cook methamphetamine.